Okay, so the recording is recording. And I already opened the Visual Studio download page. So I would suggest for the first lecture today, before we dive into actual C++, we will just take a look on Visual Studio itself and go through the installation process. So I'll paste the link where you can download it into the chat. Chat is here. Zack. And then, just as I said, the Community Edition has almost all the features you will ever need for non-enterprise usage. And it is even allowed to be used, as far as I know, in semi-commercial settings with certain restrictions to how many employees or revenue per year is allowed to do so. It's even good for small freelancers who just want to look if they can do something with C++. And of course, it's completely legal to use this version in university settings. In fact, it does not offer any enterprise Visual Studios past 2017 exactly for this reason, because why pay for something that we are fully allowed to use for free? So they just tell everyone to get the Community Edition. The only restriction with the Community Edition is that after 30 days it will ask you to create a free Microsoft account and enter the login credentials. So if you don't have an account, you can make a throwaway account, or you can make an account. That is up to you. But you will need to enter at one point the account. So when you start the installer from the website, you see this page, and what we are interested in is okay, this is in German now, but we will install the English version, the desktop development in C++, and in the additional components we will add the MFC modules. One SDK should be enough, we don't need the other one. We can add these modules here if you would want to use older versions of the C runtime, and it's usually helpful to have this on hand. I can add this, and for this application we won't need anything more, but we'll go to the languages and I will set it to English, since there is no point in working with a bad translation anyways. So I guess it will also be most helpful for everyone if then the installation that you will see will be in English. This will take a short while to download, and I would encourage you to try to get the IDE up and running along with this lecture, so that once we then take a look into the IDE itself, we can you can try it. You can try things on your own, and if you have questions, then you can ask them right away. Okay, any questions at this point? No questions? No one? Okay, so since the installation here will take a few more minutes, for the time being we could just try out my local installation of Visual Studio, or I can also load an already existing virtual machine where we already have Visual Studio running. Yeah, so if no one has so for those who don't have a Windows virtual machine up and running and are on Linux, then you won't be able to install it right away. So, but since the whole process is recorded and I will put it on YouTube, you can I think follow along quite well. That should not be a problem. I'm just looking for my old virtual machine from the last time where I put that unsorted virtual machines. This one would be one of the existing ones, so restart it. Yeah, this will take some time. Now, I'm generally a fan of using virtual machines for everything, because then if you set up a more complicated environment with additional libraries and frameworks, then you still have more or less the security that everything will work even after years, as long as you have a virtual machine. But for the purpose of this lecture, this is mostly really overkill. I just want to have a clean slate to start the demonstration. Also, another note, Visual Studio 2019 and 22 are very similar, so there is no really an issue if choosing any of those, so you can select whichever you want. I would recommend, of course, using the newest one as we are installing here, but since my old virtual machine has here still the I need to activate that. I need another account. Okay, can I do that? If there is a Visual Studio 2022 for Mac, then it should be fine. Great. What was the password? 'Nein, will ich nicht. One moment, please. That is the installation of the new probably will be done before we can use the other one. Apparently, if you use a disposable account, then it will ask you at some point to re-verify it if you haven't used it for anything else in the meantime. Yeah, that is not working. I have just discarded the window. Let's see if it works without it anyways. Yeah, it works. Okay, so they say that it will exit, but it doesn't exit. So when you start Visual Studio, this is the screen you are presented with nowadays, and here you can select whether you want to open an existing project or create a new project. So for our purpose, we'll just create a new project, and we'll select a console application. So here are usually types which you have selected in the past. So if you don't have anything in this list here, you can either start typing at the top, and then it will give you results for which project types are available that contain the keyword, or you can just try to be more scientific about it, and you select the language type, then you select the platform, then you select the additional checkbox, and then we go here for the console application. For the purposes of part 1 of the lecture, we will only need console application. We will not need any Windows native types of projects. So everything that I will show you in this lecture will work just as well on other platforms, and should for the most part not be too compiler specific. Okay, so there is a question in the chat. So you are not required to use Visual Studio, but it will help if you use it. So you can use Xcode if you know how to use it and are happy with it, or you can use the Qt Creator from the Qt framework. So if you use Xcode or something that I'm not used to, then you will need to solve your own issues if you have some compiler specific issue. If you use Visual Studio or Qt Creator, I can help you even if you're not on Windows with that. Okay, but as said, so let's call this test app 1. Then you create the app, and Visual Studio will create for you the solution and the project. So in Visual Studio, large projects are large collections of projects are put together into so-called solutions. And one solution, which is here this top-level item, can contain many projects. So in principle, you could right-click and add existing project or add new project. And then you could add another console application. And then you would have multiple projects. And if we go to the storage location of this, copy full path, then you will see the file structure of how it is stored. So it creates a directory for you where you have the solution file, which represents this top-level entry. This top-level entry here, and then you have for every project an individual subdirectory which contains actually 3 files, although only those 2 files, the vcxproj and vcxproj filters, are required. The vcxproj.user can be recreated at any time and is only specific to your particular configuration. So if you are sending a project somewhere or uploading it to a source code repository, you don't need to add these user files. And these 2 files pretty much represent the second level in our Solution Explorer tree. And then of course we have the actual source code, in this case just one file, testapp.cpp, which is stored under source codes. As you maybe noticed, there are some other folders here created. Those folders, which are created as part of a C++ project in Visual Studio, are not automatically represented by the actual folder structure on your hard disk. With other languages in Visual Studio, like for example with C#, it is different. There, the folder structure is always represented one-on-one on the hard disk, and if you are moving a file around here, it will be moved on the hard disk. But for our use case, for just C and C++, you have to either use the standard folders or create your own folder structure, and then if you want to move a file, then think about moving it out on the actual hard disk as well, which is a bit problematic, because if you do it, then Visual Studio will not track the chain. So effectively what you would do is you remove a file, move it to the other folder, and then re-add it into the other folder. The 3 default folders created here are made with a purpose. So in C++, most of your source code will be split into 2 types of files. One is a C or CPP file, as you see here, and the other will be a header file. This is something which is rather specific to C and C++. Other languages don't use separated header files, they just have the source code files and nothing else. And the idea with a header file is that it allows you to define things that your source code files need to know about, but without actually defining all the informations or providing all the source code. You just provide the interface definition. So we can make a small example of it. Although before we do this, let's start with something even more basic. So if you create a project, a file like this will be created, and there is always this main function in which the execution in a C++ application starts. So how function works in detail and on the low level, close to the machine code, then that we will take a look on later. But for now, just to roughly demonstrate how C++ works and assume some basic programming knowledge. So if you have questions, you can ask at any point in time. Generally, in all programming languages, you have functions which execute a certain piece of code and can optionally return some result, and you can invoke functions from other functions which then invoke functions, so you can have a certain level of recursion. And with the C case we can demonstrate it. So let's create a function, void, and the function will, let's say, give it a return value, and the function will just return a number, and in this case the number 1, myfunc1, let's call it. Now if we try to call this function here and try to run it, you will notice first of all that even now, before we, okay, it's not complaining, the IntelliSense Visual Studio has a function called IntelliSense which tries to tell you whether your code is correct before you compile it, and it sometimes works, sometimes not. So if I just type here function2, then it will really underscore it because it sees that there is no function2. If I type function1, it sees, there is a function1, so it will not underscore it, even though this code written exactly as written here will not yet compile. We can test this out by trying to compile it. And the reason for that is that normally, you see, it doesn't find my function1, despite the fact that it's here. In C and C++, the compiler always expects everything that is being used to already have been defined. So in case of a function that we want to use, we need to define the function prototype. We don't need to provide the whole function before we use it. Otherwise, we could not even, for example, call ourselves if you would want to make a recursion or something. But we need to tell the compiler upfront how the function1 will look, and whether the function1 is here or somewhere else doesn't matter. So we can add another source file. Let's add a source file here, and source cpp. So first of all, we will of course compile this use case, and well, it compiled, so it created the application. But if we remove it and move it to the other file and put it here, it will work as well. So if we compile it again, it will work as well. And now the interesting thing is what happens if we define the function somewhere, but actually don't have the function being actually implemented. So in C++, if you want to comment something out, then you can either use slashes, normal. Then you have a single line comment. So everything that starts with a // it doesn't need to be like a line. You can also add a comment to an existing line, will be meaningless. So everything that you have after the 2 slashes is just text for you to tell you or another programmer what you intended to do, and it is recommended to use those sort of comments a lot, because it helps even yourself to understand what you wrote 10 years ago. And there is another type of comment called a multi-line comment, which starts with a / and goes up to / in however many lines. The only way to break out of it is to end the comment. So, but going back to our initial example, if we disable the function and then try to compile, it will still, if you look on the output, successfully compile source cpp. Okay, let's recompile it completely. So one thing that the Visual Studio does to save on compile time is it only compiles files which have changed. So as we saw before, it did not compile test1, it just compiled source because we edited source. But if you press on the project and then select rebuild, then it will discard all previously compiled informations, and it will restart from the beginning. Let's quickly see if the installation is done. Okay, this already is done, so we will be able later to switch quickly to our already installed Visual Studio. But let's continue here. So as you see, both source files compiled just fine despite the fact that the file is missing. And the error came at the very end when the linking stage was invoked. So in C and C++, when you are compiling your source code to a binary, this is usually a two-step process. In the first step, every individual C or CPP file is compiled to a so-called object file, which we can see here when you go into the created so it creates a couple of directories like this debug directory, where then your object files are stored. And here you see we have test app object and we have source object. So these files contain pretty much the so-called, so let's say half compiled representation of what you have written in your C or CPP files. When I say half compiled, what I mean is the code is close to machine code, but it is position independent. And pretty much if you would create a library, then just the library would be a collection of these object files. And in the second stage of the process of creating an actual binary, the so-called linker takes all these object files, which each of them can do its own stuff, but whenever there is a function invoked from anywhere, it does not yet really contains the function invocation. It just contains the name of the function that needs to be invoked. So the linker then, when it's linking the whole application, will look, aha, we have here function 1, so let's look into all the object files or the included library files if there is this function defined somewhere. And if it is defined, then it will actually then insert the address of the function at the right position to the final code. So such errors can in fact be quite tricky to debug, because there are, as you see here, the function name, for example, is not exactly what you wrote. So you have a so-called function decoration, which is done in order to differentiate how the function is called. And into function calls we'll take a closer look later, but enough to say that you can have a function with the same set of arguments and the same return value, but with additional parameters when you are defining the prototype. And depending on the parameters, the function will have to be invoked differently on the machine level. So of course, I said in the simple case, you just see, aha, okay, I forgot to define the function, so let's quickly do it, and then everything will compile just fine. But there are certain edge cases where, especially when you are using libraries provided by someone else, you might run into linker errors, and those errors can occur if the header files provided for these libraries are not well defined enough. So this is just to keep in mind. But for now, as said, we have successfully compiled the function, the binary, and usually the way Visual Studio is set up by default is that it creates you another directory where then the binary file with the resulting program resides in. Where exactly those files end up, so the final output as well as the intermediate output, is something you can configure using Visual Studio's project properties. So just go to General, and here you have Output directory. This is where your final result goes in. So here, as you see, solution dir is a placeholder for the directory which contains the solution file. And of course, here we can select different platforms. So, for example, for 32-bit Windows, the default is that it only contains solution directory and configuration. And the default for later is that it also contains here the platform. So if we switch here to 64-bit and compile again, you will see that the intermediate files will end up in a slightly different location. So now you see we have this x64 directory where in turn the debug output, the debug configuration ended up. And here we have the same behavior, it put it somewhere else. What is recommended? Yes? Someone said something? Yes? I just wrote. Yes, so I just wrote the definition before I use the function. This is all that is needed to tell the compiler that this function will exist somewhere. And when it then creates the object file, it knows, okay, this function will exist, hopefully, and that's all you need to include it. What is customary to do, of course, instead of defining your functions in every single source file, is to just take the definition and put it into a header file. So the files that end with an H are so-called header files, and they are not being compiled to code directly. Instead, what you do is you include them using a preprocessor definition in your source file. So that if you have 100 file functions in your project or more, then you can have them in a couple of header files, and then wherever you need them, you just include the right header file. And then if you try to compile this as well, it will find this. And a interesting side note with regard to header files is, and this include mechanism, is that this include basically what it does is on a intermediate step while compiling the file, it really just takes the whole content of your header file and puts it at this place into your source code file. Of course, this intermediate state is not like explicitly shown to the user, so there is no edited CPP file generated anymore. Some very old compilers in fact did that, but nowadays this is not longer customary. And there is another thing that you have to take into account, namely that if you would have, for example, include the header twice and then try to compile something, okay, now it will actually work, but if it only works because by default the compiler, when you the Visual Studio IDE, when you are creating a header file, adds you this preprocessor definition pragma once. If you remove this thing that the compiler created for you and then try compiling it, then you will in fact run into that should be complaining rebuild. It should normally be complaining that a function is already defined, but apparently it does not complain. Okay, an older version of the compiler would complain it. I mean, we can, I'm sure, force it to. Okay, it's not complaining. Well, it only searches the header files which you have included. It's not automated in the sense that you just have to create a header file and then it will find it on its own. You have to tell it which header file to include. And normally I would expect, at least with older compilers, that if you include a header file twice, then it will complain about the function already being defined. But for some reason it did not complain. We can try to set an older C standard. No, we cannot. It's that's which this version of Visual Studio supports. But normally, one thing you can do to avoid such issues if you have one and the same header included multiple times. So one option is, as I said, use this pragma once definition. The other option, which is the older one, is that you define something. First you check if and def my age, let's call it. Then you define your header and then you make so this is another feature of the preprocessor in C++. Namely, you can create like it's like a small programming language within a bigger programming language. Everything you create with this preprocessor definitions will not directly be part of your program, but if you, for example, have an if statement, so a condition, then if the condition is fulfilled, then the following code block will be part of the source code which actually gets compiled, and if it's not fulfilled, then it will in fact be disabled, and Visual Studio solves it by showing it in gray. And the trick here is that you say if my age is not defined, then define my age, and then all the rest is also done. And if you then would have the same header included a second time, then you see here the second time all the code here will be disabled. And you can use the preprocessor to do also other things. For example, if you, in this example, if you want to have like a, let's use the header for it. If you want to define some variables in C++ or C, you could of course use an enum, but this is not always what you want, especially if you would want a string variable, for example. So what you can do is you can give some name, define, and then you write, hash define, then you write a name, let's say my const, and then you can write any code within one line that you are interested in, let's say 1, 2, 3, and then wherever you enter this placeholder, we need to include it. Wherever you enter this placeholder, the precompiler will basically just take the code from here. In this case it's trivial, but it will copy it and then it will insert it for you in the code before it does the final compilation step. And you can use also some more complex. So for example, you could also write something test, let's call it define test 1, or let's call it you can specify arguments b and then a plus b. And then if you, for example, would use this definition here, add num, say my const, and 100, and then it will first look for this, it will insert this piece of code, and well, it will replace a and b with this and this. Then it will check again in the second pass whether there is something for my const defined, which is again, so it will then, in the end effect, this will internally just evaluate to 1, 2, 3 plus what was it, 1000. There is one limitation at this point which needs to be taken into account, namely that this recursive evaluation of the preprocessor only works for C++. It does not work for just C. So in just C, you can use the first thing, but a more complex preprocessor-based definition will no longer work. The preprocessor is a useful tool, but except for include statements, it's optional, so you don't really need to use most of the other mechanisms that the preprocessor allows you. For example, one very nice thing is that you can just define if 0 hash end if, and then just disable a code block. And the advantage of this over a multi-line comment, for example, is that if we if you would have a multi-line comment, oops, and then something else, blah, and then let's say the same function invocation, and you want to disable the whole code block, your multi-line comment will always end at the first end marker. It will not wait for the second one. While if you, instead of multi-lines, would really use like if 0, I need the hashtag, if 0, then again if 0, then here and if, then it will work. And if you change this to 1, then it will enable only one code block. The major difference is that it expects you to have everything that is within this code block to be a valid C syntax. So with the comment, you can just write an essay inside of it. It really doesn't care. With these ifs, it really is recommended to just have valid code. Although if you would have here some something invalid, then it would still compile, because the compiler will effectively cut this out anyways before it compiles it, but it's not recommended to do it this way. Okay, and also this preprocessor thing is something quite C and C++ specific. You will not find such a construct in other languages, at least not in the mainstream ones. Okay, so since our installation has already here finished, we'll soon switch to the other VM, but just to tell one more thing about Visual Studio and how these projects generally are managed. In the toolbar you see here two drop-down menus where you can select first a so-called configuration, where by default the Visual Studio IDE creates for you the debug and the release configuration, and then you can select the architecture. So first about the configurations, release means that the binary that results from the operation, the binary that will be generated by the compiler, is intended to be deployed to your users. So it's pretty much what is all the software that you get when you download anything off the internet. It will work, it should not crash, it should have good performance, low memory usage, etc. But it will be missing a large amount of optional internal runtime checks, and this is what the debug configuration is for. So when you are developing an application as a developer, or are releasing your files to a closed or at least limited group of testers, you might want to use this debug configuration. In the debug configuration, the way it is configured by default by the Visual Studio, it will include a large amount of runtime checks, and it's a significant amount. So there will be a large performance penalty in certain operations within a debug build. So if you would want to find performance issues with your application later on, and not find other programming mistakes, it is recommended to do your profiling and performance analysis on a release build, not on a debug build. While as long as you are programming the application and are at risk of introducing bugs and memory corruption and stuff like that, it is recommended to use the debug option, because there a large subset of common programming mistakes can be caught by the runtime checks. So one example, for example, would be since in C and C++ you have to manage your memory on your own. It is easy to either try to use a memory block which is too small, so you allocate, let's say, 100 characters but write 120 to it, and there is nothing that will prevent you ordinarily from doing so. Hence, when you are programming, you should take care to either not directly try to directly access memory, just already use already programmed functions which are checked to be secure. There are examples like a memory copy function. So in C you have the memcpy function, which just copies one memory block to another, and it copies the amount of bytes that you tell it. And there are secure variants of those copy functions which expect you to provide not only the amount of bytes that you want to copy, but also to provide the size of the memory block which you are copying to. The idea is that you will not make the same mistake twice and provide an invalid memory size. Because, for example, if you are copying some memory, you probably are not writing the size by hand into a program, but you will have some length that you add to another length that you add an offset to, and so on. And then you end up with some length which within your initial assessment should be fine, because you didn't maybe thought that a user would enter a string longer than 100 characters somewhere because you told the user to not do it, but the user will still do it. And of course, now if you are using a save function to copy a string, in which in addition to the amount of characters you want to copy, you also have explicitly to specify the size of the buffer you are copying to, then this error will be caught. Such functions work also in a release build. So in a debug build, the methods to catch such errors are different. Namely, when a memory block is allocated for the inside a debug build, the debug allocator will fill it up with a known pattern, so that if you would use somewhere and some uninitialized memory, which is, by the way, another common mistake, that you are using memory which just contains garbage. In the debug build, it will always contain the same bit pattern, so it's easy to spot if such a mistake happened. But going back to the mechanism that prevents you from overwriting past the end of your buffer, is that it will not only fill the memory block that you have allocated with a given pattern, it will also add special markers at the begin, at the end of your memory block. And once you are done using the memory block later, it will check whether these markers are still intact. If they are not, then it means that you have at some point written more to the memory block than the size of the memory block allows, and then you will get a heap corruption exception thrown by a debug build. It will unfortunately not necessarily tell you where the mistake happened, but it will tell you that something bad happened, so you can debug the issue further and find the problem. Another thing, yes? It's not in files. It is only within the RAM of the computer. And if you ask the debug allocator to give you, let's say, 100 bytes, then the allocator will actually allocate, let's say, 120, and the first 10 will be filled with some pattern, and the last 10 will be filled with another pattern, and you will get the address of the 10th byte of the actual block that you have requested. And then if you return the memory to the allocator and tell it to free it, it will check those markings. And the other thing is that if you tell the allocator to deallocate some memory, then in the debug build it will again overwrite all the memory with these, like d for deleted. So if you later would reuse a pointer to this memory, then you will just run into most likely invalid data, so the chance that you spot the error or that it will cause an instant crash is much higher. And those operations like filling memory with patterns, checking for it, it takes generally, well, it is wasteful, basically speaking. So one of the most badly performing things in a debug build is the memory allocation. So if you have a debug build and you see that, okay, it is slow, but you see that it's slow with regard to memory allocation, you can be quite sure that if you create a release build, this will be fine. And those configurations are well configured, so you can go here in the project settings, and you can pretty much set all those settings for every configuration and every platform or architecture individually. So to go back to this example with the debug and release, for example, the optimizations. If you look on the debug configuration for optimization, you see that optimizations are disabled, inline function is set to default, intrinsic functions are also disabled. And then if you switch to release, you see that it changes. It now wants to optimize for maximum speed. It wants to use intrinsic functions. You can also change this here to optimize also for speed, or you can optimize for size, so that your binary is smaller but not as fast. And one of the major issues with those optimizations with regard to debugging is that if you build something in the debug build, then the code that the compiler will generate as a result of your code that you have written in your application will be very letter by letter or statement by statement representative of what you have wrote in your functions. While if you compile it as a release build, then the compiler will think, okay, so we have here a few variables, and we copy this there and that here, and maybe if we remove this variable, we can save on a few copy operations, and this operation is irrelevant anyway, so we just throw it away. So the amount of code will be reduced, but in the end, it may result in your variables to not all of your variables to be represented in the machine code at all. So it makes debugging harder. And another issue at this level is that the way how CPUs operate is that internally they have an extremely small amount of memory called registers. So for example, 64-bit AMD 64 or Intel AM64 architecture, which are pretty much the same thing, have only 16 registers, 64 bits each. So it's an extremely small amount of memory, and all the operations that you are doing within the CPU, you are doing on these registers. So as soon as you want to access memory somewhere, you need to copy the data from your RAM into a register, then do something with it, and then either copy it back to RAM or keep in the register for the next operation. Now, at this point, it is probably good to say that in your typical Intel architecture, many instructions can be done directly with memory addresses. So you can just say take memory address this and add to this 5 and write the result into register AX, for example. This is not true for CPUs in generally. A lot of so-called ARM CPUs, which are based on so-called RISC, which stands for Reduced Instruction Set architecture, are all the opcodes, all the machine commands that you can use in them, except a very select few, can only operate on registers. So on the Intel platform, you can, as I already said, have one instruction which tells the processor to fetch some word from the memory, put it into a register, add something to it, and save the result into another register. On a RISC-based CPU, like the ARM CPUs that you have in your cell phones and smartwatches and pretty much every embedded device nowadays, you will need to have one instruction which explicitly fetches something from memory, puts it into a register. Then you have your individual instructions which do something with it, and then you have to store it to memory back. And internally, the Intel CPUs are in fact working in a way similar to RISC. So they will dissect a more complex operation into micro operations, which will be get it from memory, put it into register A, add 3 to it, and then do something else, for example. So, but what I wanted actually to say is that if you have variables, it is often quite efficient to have those variables just be stored in a register and not live in the RAM of your computer, at least for short calculations. And in the release build, the compiler will do it. It will remove variables from memory if it can just use registers for it. And this makes debugging even more challenging, because you don't have then a memory location corresponding to every of your variables. This is also why normally in a debug build, you will in fact have a memory location for every single variable. So every operation will be take it from memory, put it into register, do something on it, save it back. And in the release build, as said, if you have like a couple operations, it will just not do the save back as often. It will just at the end, when you have the result, do something with it, and not necessarily show you really every step. So there is a good reason to use both of these configurations. Now, I personally disable some of the debug features often because some of them are annoying. We will see this in the later lectures when we take a look into the machine generated code, especially the what was under general, I think this just my code debug option is particularly annoying because it generates a lot of boilerplate code which you don't really need. The idea is that it allows you easily to step through the program step by step, only looking on the parts of the code which you wrote yourself and skipping around libraries and external functions. But for our use case, we actually want all the nitty-gritty details, so we will usually be disabling this. Yeah, and one more thing about the architecture or platform, which you can configure here. So in this particular case, we have Win32, which is a 32-bit Windows binary. So it will run on pretty much any super old Windows version on a 32-bit processor. Or we have this x64, which is just the 64-bit version. It might be a bit counterintuitive why it is not called Windows 64, for example, or anything, just x64. The reason is in a way historic, namely the whole Windows API as we know it today is just called the Win32 API even on a 64-bit Windows, and that is so because initially the first Windows that was made was just running on a 16-bit Intel instruction set, and then when they moved from 16-bit to 32-bit, they changed the API a lot, and they called it the Win32 API, and there was really massive changes in how the API behaves. Much later in, I don't know, 2004, 5-ish, when AMD released their 64-bit architecture. Although truth be told, that was earlier already for the Intel Itanium, which went nowhere, which also was a 64-bit processor. Microsoft already ported their Windows to a 64-bit platform, but there they really didn't change the API except for making all the words or double words twice as wide. So word width and such are things which we will take a look later during the lecture when we look on the internal representation of variables in the CPU. But enough to say at this point is that the way this works is that they just make the integers twice as long. So on a 32-bit system, your typical pointer length is of course 32-bit, and for the 64-bit platform, they just changed pointers to be 64-bit, and they didn't change anything else about the API. So you can write a code in your C compiler, and then you can either compile it to 64-bit or to 32-bit, and the exact same code will compile, and unless you did some unrecommended things while writing your code, then it will work fine. So, for example, the compiler provides you data types and size types, which will change from 32-bit to 64-bit as you change the platform for which you are compiling. So, if you keep in mind a couple of very simple rules, then your code will be portable between different bitnesses. For the very old step from 16 to 32-bit, this wasn't true. They, as said, redid the whole API, changing so many things that you could not compile the same code basically. And of course here we could add, if we go on configuration, we could add an additional platform, for example ARM. So let's go for ARM. Oh, we only have the normal ARM. Okay, let's get with normal ARM, and let's copy from this configuration. Okay, and now we have one more. So now we could compile our project to work on a ARM CPU. So for example, if you have a Raspberry Pi which would be running Windows 11, then you would need to compile your programs for ARM if you want them to run natively. Okay, so as much to these parts. Now let's go back to our virtual machine, which already went to sleep because we spent so much time with the other one, and look into our freshly installed Visual Studio and how to configure it, and then start using it for some initial programming. So the plan for today will be to show you the debugger and how this works. So here we select skip for now, but as said, after 30 days it will require you to enter some account. You can create a throwaway account. This is fine, it doesn't matter which go with. So the color scheme is up to you, which one you prefer. I like the light one. I don't like dark themes, but that's a personal choice. And here you can select, so this option pretty much tells you which tabs here and there, and whether it will be on the left or on the right. There are actually some on the right here as well, you will get. I just always choose general, and you can change it fully later on. So this is not a setting that is like that limits you in a way. It just gives you an initial start configuration. This will also ask you only once at the beginning. And once this thing is done, let's hope it will not take too long, we can again create a console project here. Okay, yeah, we can close the installer, at least for now. And then ascend. Initially the list on the left will be empty. Also here the list on the left will be empty, and then we just go for the console project. We select next, we enter let's call it my first app. Oh, my test app. Let's go with test. My test app. Then you can also select where you want the files to be stored. By default it goes to your user profile source repositories, which is fine. If you specify here a different name, this will be the name of the SLN file. So if we look in the already created project, that will be the name of this file, and I think also the name of this directory here. But let's also just stick with SLN, and you could of course select this option, which will then pretty much just take this content here and put it directly into this directory, which might be in some cases okay. I prefer to just leave it by as default, because if you at some later point add additional projects to your solution, then you will be happy to have them separated into individual subfolders. And if you are wondering when would you need more than one project in a solution, this can happen quite easily. For example, if you want to create a library and move some of your functions that you want to use in multiple projects, then you would here just add some library. You can perhaps download a library from the internet that you want to use in your project. Depending on how the library is deployed, it might be the easiest thing to just add it to your solution. So there are many cases. Or if you are creating a more complex application which will have more than one binary, like one binary for configuration, one binary that runs as a server, another binary, I don't know, to clean up something, then you would also want to have multiple projects in one solution. Another nice thing just to be said here is that if you go to properties, you can configure the project dependencies. Now in this case, of course, we don't have any because we have one, but if you would have some own libraries which you have to compile before one of the other binaries can be compiled, by setting up the dependencies, you can ensure that the compiler will know in which order to compile things to avoid you getting an error because something was not yet compiled and is being compiled right now. But coming back to this case, we will create our test application. That should not take too long. And then we will take a look into all the settings in Visual Studio, of which most in the other Visual Studio I already have set to how I like them. But to a certain extent, this is always up to the user to select which options one likes. So for example, one thing Visual Studio does is when you start typing something, like something that, well, for example, a string or a comment, it automatically adds the closing expression for you. I find this mighty annoying. I always disable this. Another thing is that if you screw up the formatting, if you type the semicolon, it will automatically format the code block for you, or if you close the code block, it will also do the formatting for you, which is fine. I don't usually object to it, although sometimes it's also annoying because you might want to have a more custom formatting and then it will break it. So, and of course, if you are pasting some code, it will also format it for you. So maybe some of those things one would want to disable as well. And there is another thing here, this external dependencies folder, which is just huge, which is pretty useless as well. So we will now take a look how to disable all those things. So we go to options, and we can just type things we want to look for. This was advanced. So disable external dependency folder. We can disable this here. Then we can select track. Trace. No, where was that? Probably it was also somewhere in the other tab. So what I want is, if you go again to the configured one, that if you are switching files, I like here the tree to automatically select the file which I'm working with. This is not on by default. This is also quite annoying, and it's called something like track or trace active item. Where was it? Yeah, track active item in Explorer, in Solution Explorer. So we want this, and then all language out. Where was that? Okay, so automatically format statements when we type semicolon. I don't want this. I will keep the formatted when you make the code block end. This is fine. And when pasting, I would select just to indent, but not to format. But this is not everything I would like to set for me. Or is it? I want most important to disable the automatic completion of these expressions. Since I don't set those things too often, I always forget where to find them. Telecode. That sounds. No, in telecode we should not need. This one. I think now it should be off. Yep. Wait. Yeah, this worked. This works. This works. Perfect. It doesn't autocomplete things anymore. But as said, this is up to you. If you like this autocompletion or don't want the items to be tracked in this tree, you don't need to do these changes. But as said, I find it quite annoying. So I always configure it this way. The next thing which we will need to configure in the options will be the debug symbols. And then we will try out the debugger next. So we go to symbols, and you can select Microsoft Debug Server. It tells you that it will need storage and it will download things off the internet, which is fine. And then here, load all modules, unless excluded, that sounds fine as well. And we should specify a symbol cache. Since those symbols are quite big, sometimes we'll just create a folder on C. And if you would be debugging, for example, on Google Chrome or on Firefox or on other open source oriented projects, you can add here additional symbol servers. So you can just click on plus, and then you can add. No, oops, damn it! I think I pressed escape once too much. Yeah. Okay, so we want this. This it remembered, but it forgot our path here. So let's reselect it. Symbols. Load all modules, yes, and Microsoft Server. And also one other thing. Somewhere we can, I think, globally disable this just my code thingy. Here, enable just my code. Let's just disable it globally. And let's disable this also. So this feature here, continue and hot reload, what it would allow you is that if you interrupt the execution of your application and then change the code, the actual source code, and then press run, then it would compile the code and try to resume execution in a way that would work with the new code from there on. I see how people might find this useful, but it also is prone to just cause trouble. So it's better to just kill the application, change your code, compile it, and start it again. So we will disable this here as well. And now, well, we can recompile the application. As you see, Visual Studio 2022 by default selects the 64-bit platform, no longer the 32-bit Windows platform. Also, another thing to be said about Visual Studio 2022 is that this is the first Visual Studio which itself is a 64-bit application. The old 2009 up to 2019, the application itself was mostly 32-bit. When I say mostly, I mean the application as such is 32-bit, but it has helper processes which are 64-bit. in the Visual Studio 2022, really everything is 64-bit, which is helpful for very large projects. It has also some downsides. For example, it will notoriously consume more memory than the 32-bit version, but since we are young and we want to learn for the future, we'll just use the newest one. There is no really good point to stick to old versions of compilers and libraries for new projects. If you have an old project, I would not update it to newer compilers or newer libraries unless you have to, which depends on the scope of your projects. The have to might be always. So if you have something that interacts with arbitrary user input or arbitrary data of the internet and you need to avoid any potential security exploits, then you might be forced to always update your libraries, which then will at some point need newer compilers, so you will be forced to keep with the development. But for the typical lab use case, you have your program, only your coworkers interact with it. It's not open to the internet. There is no security downside of using an old library that works, even if it has a known security vulnerability. As said, for public-facing projects, this should not be done. So you should always try to get all the necessary updates for your project, as long as you suspect your applications might be a target for attackers. But anyhow, so we wanted to compile this, or did we build? Okay, it's already built, and when we then, no, it's building. Okay, and once it's built, it tells you where it put it. It does not tell you what the intermediate files are, but as you see, it created this PDB file. PDB stays for, well, it's an abbreviation of Program Debug Database, and this is what contains the debug symbols. So debug symbols is a term which might sound a bit misleading, because basically what it contains is information how the generated machine code relays to the source code which you have written, even if the optimizer then throws away lines of your code. Then of course the association will no longer be line by line, but it will still allow you to know all the names of the functions, although the optimizer might even remove a function. So if you have a very short function which you are invoking from somewhere, jumping to a function to somewhere just to make an addition, for a very simple example, is wasteful. It's better to just take the code from the function and paste it into your invoking function, and then just replicate this code 100 or 200,000 times, however often you are invoking those functions, especially if you select the optimization to optimize for speed and not for size. And this, by the way, is something that changed a lot in the last decades. Historically, CPU time was the thing of which you, when in doubt, have enough, because you can always wait longer for the result. But memory was really what is limiting. So the old systems mostly wanted to optimize for the smallest memory usage, even if it was at the cost of a slightly longer execution time. Nowadays, we can have hundreds of gigabytes of memory, but the CPUs are not longer getting as much faster as they used to get in the first decade of the 21st century, or even before that. We kind of hit a hard wall with regard to the CPU speed for a single CPU core. Now, if we compare the most modern AMD Ryzen Zen 4, so Ryzen 7000 Zen 4 architecture CPU with some Intel core from 10 years ago, we are close to a doubling of the speed, but it's just close to, and it's just a doubling. Before that, you had like a doubling of the speed every 2 years. What nowadays doubles is the amount of cores, but if you have a problem which is just a linear, a problem which is written in a way that you can just solve it step by step by step by step by step, then you can have 20 cores and you will still only be using one of them. Nowadays we have as many cores as we want. We have gigabytes of memory, but the execution speed of a single thread is the most limiting factor. So nowadays all the optimizations which are being done are being done to optimize the single-threaded execution of code, since it is not really possible to have a automatized it is not really possible to automatically optimize single-threaded code to run on multiple CPU cores. In more high-level languages, you can have such tricks used, but if you are writing something low-level like C or C++, then if you want something to run on more than one CPU core, then you have to do it yourself. The optimizers of the compilers will not help you with that. So this on a small detour to how these optimizers work. And as said, this PDB files is where then the compiled code is documented in a way that the debugger can then point you to your own functions. And for example, Microsoft, while the Windows operating system as such is completely closed source, they are in fact offering the well, not fully fully featured, let's say, debug files, but they provide you with debug files which at least contain all the function names and some of the structure definitions, so that if you are debugging some of your applications and then you see that there is a crash in a part of Windows, you can at least see where it happened and get an idea maybe why it happened and which wrong parameter did you provide to it. So and of course, if you include some symbol server for Chrome or Firefox, then you will have just the full debug files because it's open source anyway, so it does not matter. So I think I talked already a lot about debuggers, so it would be time to try one out. So let's have a very simple program. Yes. Since they bought GitHub, they added support. Before that, so if you go to Options Source Control, you can select already a plugin, and you have GitHub. Then you have this Microsoft Visual Studio Team Foundation server. And like in the past, before they bought GitHub, they only offered this. Once they bought GitHub, they also offer well, Git. And but since Visual Studio is very extensible, you can install plugins to use, for example, SVN. You don't need to use Git. You can use SVN. You can use CSV. So in principle it's possible. You can also have like an own Git plugin if you want. If you don't want the one built into Visual Studio. So yeah, you can do that with the modern Visual Studio. For this lecture, I think the simplest thing is you just pack your solution. So you go to your solution folder. Where do we have it? You select this and this. You select send and unzip, and then you go again inside and delete the intermediate output, and this is then what you can upload as homework. So we will not be wasting our time with creating GitHub accounts for everyone. You can just upload. So once there is homework scheduled in the Moodle system, you can just upload a zipped representation of your project source code, and that's it. I think it is easy enough, and well, if you don't use Visual Studio, that means more work for me because I will need to somehow get your code running for test on my platform. But well, I think there were not so many people, and the things we will do are quite simple. So I expect that I'll just copy the content of the C file into a new project, run it, and it will run. So there should be nothing platform specific. Any more questions about source code management at this point? Sure. Okay, well, the other one is small, unfortunately, but at least I can zoom in the code itself. Okay, so let's continue. So here we have an extremely trivial initial program. We have the main function, and we use the printf function to write test to the screen. And one thing to know about debuggers is that they usually allow you to define so-called breakpoints, so that you can tell the debugger that you want your program to interrupt execution once it reaches a certain line. So in this case, we obviously want to break here, and you can just press either F9, or you can just click with the mouse on the sidebar, and this will set you the breakpoint. If you want to, of course, to put more work into setting your breakpoints, you can open the breakpoint window, and then you can here add new breakpoints where you can then specify functions and addresses and also conditions. But this is rather complicated. So even if you want to specify a condition, you can just set the breakpoint where you want it, and then just double click on the right click on the breakpoint, go on settings, and then add a condition. How those work, we will take a look on later. But for now, we just have this one breakpoint, and we have here our debug and 64-bit platform, so we are ready to start our first application. So one thing, of course, is you can just press on build and then press on run, but normally if you just press on the local debugger button, it will build and run it for you with a debugger attached. So this is the most user-friendly option. Now you notice that the first start takes some time. When we look to the output window, we will see that it is downloading the symbols. So now it showed a window from Microsoft Symbol Server for all the DLLs that are part of Windows, which are now being loaded into a process. So what we also notice, at least on Windows, is that there are quite a few DLLs which are needed for even the simplest of applications to even start. And this, in a way, is a case for every operating system which has a non-trivial complexity. So also on Linux, you will have to at least load the C library before you can do anything. In the particular Windows case, you have the anti-DLL, which is where every thread and every process start execution. This is something that is abstracted away from the user. We can take a look on this later on. Then we have the kernel 32 DLL, which contains pretty much the primary Windows 32 API. And on more modern version of Windows, meaning like everything since Vista and above, you have this kernel base DLL, which Microsoft wanted to clean up their, let's say, code mess, and split functions from the Win32 API into more well-defined DLLs. So typically when you are just interacting with the normal Windows API, you will just use the kernel 32 or user or GI APIs. But in many functions which in the past resided in the kernel 32 API have been moved into this kernel base DLL. App Help DLL is just for the compatibility assistant of Windows. So this is something that helps old programs which may expect a different API behavior from Windows to still work. So Windows historically, they knew that compatibility is pretty much the only reason why people are using Windows, and if they break compatibility, they will pretty much kill their own business. So when they made newer versions of Windows, if they have seen that there are commonly used applications which use a bug in the API of an older version, they actually implemented the bug in the newer version of Windows still. But sometimes they may decide that, okay, we really don't want this bug to still be there. So what then they do is that they actually fix the bug, but they have a library. They have a library of applications, so where they can look up which applications would actually exploit this certain misbehavior, and then the App Help DLL could in fact patch some of the Windows functions only for this one process to express this erroneous behavior from older Windows versions. This is also when you go into the compatibility assistant for some application, when you can select like the different Windows versions. So here, for example, we see that they don't longer bother on Windows 10 to provide compatibility with Windows XP, but still they at least go as far down as Windows Vista. So this App Help DLL is still needed to some extent. And then the next thing we load is the VC runtime. This is the first DLL which we load, which is not as such part of Windows. Although it is provided by Microsoft, it is a part of the runtime for applications compiled with Visual Studio. That said, you can compile applications using Visual Studio without actually using the C runtime library. You can provide your own runtime library, so to say, if you want. This is something that in very special cases might be necessary, but I don't expect us in any reasonable lab scenario to actually need to write a program which does not include the standard C runtime. And the CRT base T is just another DLL which is part of the C runtime. So this one is loaded, and this DLL is quite small, and then it loads this one which contains the actual implementation. Another interesting thing to know at this point is that Visual Studio in the past, like the older versions, 2002, 3, 13, 15, each version of Visual Studio came with its own C runtime version. Starting with Visual Studio, I think 17 that was, Microsoft moved to a unified C runtime API, such that you just have one C runtime API installed on the system, and it doesn't matter for which of them. So if you have just the C runtime for 2017, you still can run an application compiled with Visual Studio 2022. Or if you only have the newest C runtime, it will also work the other way around, so that it is much easier to deploy applications nowadays because you have much less different dependencies. It also helps you with libraries, because historically, if you had a library file which was compiled with one C runtime version, your project needed to match this runtime version. So you might, if you got from a device manufacturer, let's say you have a laser or a power meter or any sort of your lab equipment that you get, and then you get some library that you can use to communicate with this device. If this library was old, then you were limited to use only an old version of Visual Studio, or you would have to split your application into multiple processes and complicate things. Now, with this unified C runtime, as long as it is not super old, i.e. before 2017, you can include such libraries and it will link just fine. So this much to this, and then the first thing we will take a look is the call stack. So if you already have any experience with programming, you know that programs are made up of functions. The functions can call other functions, and they, except of calling other function, can do some internal stuff. And if you call, if a function calls another function, and so on, then what it generates is a call stack. So you have pretty much the list. The first function that started in this process is, as I already mentioned, in the NTDLL. This RTL user thread start. This function then invokes another function in the kernel32 DLL, base thread initialization thunk, and then this function will look up the entry point in our actual application. So in this case, the main CRT startup function, and from here on up to the top is the code that the compiler generated for our application. Although the code that we ourselves wrote only starts here in the main function. These different initialization steps here are used for various housekeeping tasks. For example, if you would define some static variables. So a static variable is something that is not bound to a particular instance of an object. What objects are, we will learn a bit later when we take a look on C++. Or if you define a global variable, which is pretty much the same as a static variable in this context, when you define it, you can assign an initial value to your variable. And this housekeeping code is what will write these values to those variables before it invokes your main function. So if we, for example, would have written here, let's quickly do that, underscore true. So the name of a variable can contain lowercase letters, uppercase letters, underscores, and numbers. Although it cannot start with a number. It must start with a letter or an underscore. And it is customary when creating variables to use prefixes for them. So G underscore is for global, M underscore will be for a member of an object. But this is up to you. You cannot name them however you want. We will take a look into variables in the next lecture in more detail. Oops. But now just to use the variable in the conditional condition. So if we have a code like this and we run again, we expect our variable to already have a value, and this code is what will do this value assignment. So in this case, we can already see the next nice feature of the debugger, that when you move the mouse over any variable, it will tell you its name but also its content. And here on the right, on the left, you have a list. So auto contains the variables that the IDE thinks you are interested in. So if you have a function of 100 variables, it will show you only a few here. You can have locals, where it shows you only all the local variables. Unfortunately, we don't have any since this is a global one. And then you have watch, where you can just define variable names which you want to always see. So if we add this one, we'll see its value. And you can just type as many as you want. We can also add one that doesn't exist. Then we'll just tell you that it doesn't exist. But if the interrupt would break in another function where it exists, then it would actually show you the content of it. Of course, the way this interface works is it's made up of panels, so you can just move them around wherever you want them. You can also drag the tab itself into either a window or a new panel, or back where you took it from. So as I mentioned earlier, where you select general, C++, web development, etc., it just impacts how these panels are initially laid out. You can move them as you want, and also the layout of the panels is stored globally. So when you start a new project, it will always start with the same panel layout you set up in whichever project you worked the last time. So this layout of the window is not part of your project configuration or anything. Okay, but as said, so we have this call stack here. How the stack works, we'll also take a deeper dive into later. But the most important thing to know is that it simply shows you the history of function calls up to the current function call. And the next thing we'll take a look onto is the disassembler. So as said, normally you would just want to work with your source code, but since we are a low-level course, we want to know how the machine code looks. So if you go on debug, then you go on Windows, and you can select a lot of different windows. So we selected here this disassembly. You can also select registers, and you also can select memory. And for memory, you can select up to 4 different memory views if you want. Call stack we already have. Threads we don't need right now. Modules we don't need right now. Modules would be a list of the DLLs which are loaded. Processes we don't care because we only have one. The immediate one we already have here. So let's just go with memory one, and I like to put memory also on this here. And where did I put the registers? Okay, the registers are already here. So these are all the registers available. As you see, it's a really small amount of memory if you think of it this way. But it's not something that is really limiting us, since when we are writing code, we really just care about the amount of RAM our computer has. And of course, here the memory itself. So obviously, this is mostly unintelligible unless you are really used to reading it. But it's sometimes useful to have it. And the most important thing is for us will be the disassembly, which let's put to the side. So as you see here, it shows us also the code from here, so we can configure what we want to show. We can add the code bytes, so it will show us the memory content. It already shows us the address. We can disable source code if we don't want it, then it will just give us the function names, but we want to see the source code for now. Symbol name is, as you see here, when you have an address of a function or an address of a variable, you can select whether you want to actually see the numeric address or whether you want to see the name of the function or of the variable which will be used. And in this particular case, it actually then shows you still the address, so there really is no reason to not show it. Line numbers, I think we don't care about, since why not? Let's stay with everything. Okay, and as you can see here, this rather small amount of code has been compiled to quite a few instructions. What they do and how this works, this is something that we will take a look in later lectures in detail. For now, I just wanted to show you the debugger and how to get to the debugger. Yes. So as you see, just on a general note, at the beginning of the function, it will initialize some things for us. Then it still does something with this just my code thing, which we can disable later, and then it starts doing our code. And then once the function ends, it adds so the initial part is called a function prologue, and the thing that happens after the function terminates is called a epilogue. Yeah, and the next nice thing about the debugger is that it allows us, as already mentioned, to navigate through the code. So in this case, it's rather boring, but we could actually try it. We will minimize this window for now. Actually, you can click this pin icon, then it will be... Huh? Doesn't that collapse? That should collapse. Okay, it doesn't want to collapse. So some of those things collapse. Just find this one. Okay, we can not collapse every window. Fine. Wurscht. Yeah. So for the debugger, we have here some control elements. So we have obviously a stop, a break. So the break button, which is now grayed out, would allow us, if the application would be running and we want to break it wherever it is right now, then we can use break. It's pretty useless, to be honest, because the only use case I can think about where this really helps you is if you have a situation where your application is in a deadlock, and not a deadlock because it's waiting on some synchronization object, but a deadlock because it's spinning in a spin lock or executing an endless loop. This is pretty much the only useful use case for the pause button. Or if you just want to break the execution anywhere and then set breakpoints, and then you resume and wait for the breakpoints to hit. But you don't really need to break it. You can just set breakpoints while it is running. So really, there's just the one use case with breaking into some endless loop that you don't know where it is. And of course, the stop button just terminates the execution. You also notice that the menu bar changes a lot if you start the project, so it adds some additional options. We can add here the build menu bar as well, and for the debug one, you can click on here, add remove buttons, or which one was it? Was it this one? One of those allows you to add a button called hex, which changes the representation of numbers in the display to hexadecimal ones, which is actually quite useful here. Hex. So, I mean, for true and false, it probably will be meaningless. But if we would have a numerical representation, it would allow us to switch between those. But anyhow, so the next buttons, this one is a step into. So it allows you to step into the execution of a function. So we can actually do it. And then we end up in the actual printf function, which is part of the C runtime that Microsoft provides. And then using either a step into, because if there is nothing to step into, it will just step over. Or we can use the step over, which then, for example, here we have a function invocation. If we step over, it will not take us inside the function, it will just jump around it. So it will execute the function, and then we break the execution once the function finished. And there is also the last button, step out, which will execute the current function until it is done, and then just break once we are done with the execution. So the debugger is these are the basic functionality of a debugger. This is the basic functionality of a debugger. It allows you to break execution wherever you want. It allows you to step through the execution with as fine granularity as you need. So you can even go here and really then step single instructions, individual CPU instructions one by one. Or of course, if you are in your code, you can step. Usually, it will here step by line, no matter how much code is in a line. So if you write a lot of code in a line, then you can step over it with one click. one thing about C that I forgot to mention is that C++ does not care about line breaks mostly, and it does not care about white spaces mostly. There are certain edge cases, but generally you can write your whole program in one single line. Okay, this one would care, so the preprocessor definitions are a bit picky, but this thing will be just fine. It will compile to exactly the same code. Sometimes this can be used to make the code more readable. So a code is unreadable in there are many scenarios when by two general rules with regard to writing code, to the quantity of code and its readability. If you write a huge amount of code to do something very trivial, then the code becomes highly unreadable, because if you don't know what the whole code block does, you need to study it, understand it, and then you say, oh, it just adds two numbers to each other, for example. It just in a super convoluted way. So this is not something you should do. You should try to use as little code as you can while not falling into the second case, where the amount of code is, if you push too many operations into one line, then it also becomes unreadable. So you want to keep every individual line in your program to be simple enough that if you look on it, you know what it does. You don't want to unnecessarily spread it over too many lines. So, for example, C++ puts all your different program control flow structures like ifs in code blocks. So you could always write something like this every time you have something. And if you have an else, print blah, this is unnecessary. If you only have a single line to execute after your if, it is reasonable to just write it this way. And what you also can do is, if you would have a lot of arguments to a function call, for example, you can break them into another line. So what you also want to avoid is to write code where you would need to scroll left, right all the time to see what it is doing. Now, obviously, this is something which is highly specific to on which screen resolution you are developing your application. So, like when you look on very old applications from 20 years ago, they all were really tiny and made to fit on something that had like 800 pixels width. Nowadays, most of us have at least Full HD screens, if not 4K screens, so you can cram in much more text. But you should try to keep the length limited to some reasonable amount, just for the better readability. Yeah, that about that. And one comment with regard to preprocessor definitions, since they are not since they care for line breaks. So like in normal C, you everywhere put a semicolon at the end of your statement. This is how it knows that the next thing is starting now. With other languages, they just look for a line break or something like that. Or like in Python, it depends on the indentation and then a new line, etc. But in C, the typical statement delimiter is just a semicolon. But this is not true for these preprocessor definitions, which I already showed you earlier. In them, you just you just write something, and it is customary to write your preprocessor definitions in uppercase, but it's not necessary. You can start it with an underscore, you can make it lowercase. By the way, if you want to switch between lower and uppercase, Control Shift U makes uppercase, Control U makes lowercase, whatever you have selected right now. You can actually view and edit and what was that? Probably advanced. Yeah, here. There is a huge amount of different formatting aids that will help you to nicely format your code when writing. Yeah, but that's much to this. And assuming you want something to be, so you want a multi-line preprocessor definition. So let's say x, then you write, let's say, int x is equals 1, 2, 3, semicolon. Then you use a backslash, and you are not allowed to write anything after the backslash. You have to have a line break, then some spaces which don't matter, and then you can write your next line and your next line, and effectively the whole thing will be collapsed into one line and then inserted into your code. But for you it will look nice, and of course the last line should not have a backslash, although if it has, just remember not to put anything in there and just continue your next code one line further down. But it's a better practice to not put a line break continue the next line here. Another funny thing about C++ in this sense is that if you have a string, then you can break it with string delimiters, and for the compiler this whole thing is just equivalent to just a string, which is quite nice, because then you can put your strings into multiple lines. Oh no, sorry, that was not right. So for example, one thing where it cares is you cannot have a line break within a string. You need so within brackets you need to have it around. And what we will later learn is generally how strings in C work. But one thing that is pretty universal also with other languages is that for example, you might want to have a quotation mark in your string, but it will terminate your string. So how do you do that? How do you work around this limitation? And one way to do it, okay, there is a question in chat in a moment to that. One way to do it is to use a so-called escape sequence. So you use this backslash character, and if you have a backslash something, then it gives it another meaning. So like backslash quotation mark means insert a quotation mark into a string at this position. So the next question of course is, so how do you make a backslash? Pretty simple, you just make 2 backslashes, which on Windows is particularly annoying because normal path separation in Windows in file name paths is the backslash. So when you copy a path from your Windows Explorer to your source code, you need to remember to replace all slashes with double slashes. In fact, in C#, which is a C-like language, which we will not be taking a look on, which I'm just mentioning for completion here, you can prefix a string like this, and then it means take the string as is, don't do any escaping, so you can actually use single backslashes then. But this does not work in our normal C. That is just for completion. And of course you can, if you want a line break, have \n. And if you ever worked with some more low-level text editors, you would notice on Windows that if you actually write a line break, it will make a I never remember the \r\n. Oops, one too much. So \r means carriage return, so it moves the cursor back in the same line to the beginning of the line, and \n means move one line up. So this actually was quite useful if you have a console like this one. If you move the cursor back to the beginning, you can overwrite whatever is here in the screen buffer. So like for some progress updates or things, it's pretty useful to just use the only \r. Although, and if you just would have \n, then it would move at this position just one line up, but it would not move back. Although Microsoft changed on that in the somewhere with Windows 10, so you can expect in more scenarios \n only to also do a carriage return for you. And in fact on Mac or Linux you just use \n, and that kind of automatically includes that there will be also a \r executed. But you still can use \r explicitly if you want to overwrite something on the screen buffer. And there was a question why to use printf instead of stdout in the chat. Well, one reason would be that stdout is not something that you can use in just C. stdout is something that exists only in C++, because the it's a class and classes and more complex objects only exist in C++. This is something which we will take a look on closer when we work with it. So which subset of features you can use in C in just C from the whole C++ set of features. In fact, historically there was just C at the beginning, and then they extended it and created C++ to be a much more complex and a object and an a in fact object-oriented language. So normal C is not even object-oriented in the typical sense of the word. C++ is, and really for the most part there is no reason to want to write something just in C, because you are extremely limited to what you can do. As I, for example, mentioned a long time ago in this lecture, like 2 hours ago, you cannot use recursive preprocessor definitions in plain C, or as it's also sometimes referred to as ANSI C. So for our use cases, we'll probably for the most part stick to using C++. The special use cases where we would want to write something just in C is, for example, if we would want to write an application which does not require the C runtime library. So then we would really write something just in C and only use the simplest language constructs they are. But it's not like a necessity. So we can, in fact, provide our own C runtime that we implement by hand, and then still use all the advanced C features, C++ features, even if the target we are compiling for will not provide a C runtime as is. A example of this would, for example, be when you want to write a driver for Windows. Nowadays, in fact, you can write a driver directly in C++. But even if you do it, you will need to provide some implementations on your own, because the normal C runtime is not available in kernel mode. So for the simpler things, like just object and classes, you are able to just use the normal C++ for a driver. But if you would want to use new or delete instructions, you would need to actually define those operators and make them use some kernel memory allocator. The normal ones will not be available. What we'll also take a look during the course is how what C++ does can be represented in a C way. So, for example, if you have a class which has functions and virtual members and stuff like that, how you could invoke a function on a C class just from C without using the recommended method. So it's a bit hacky, but it's actually really quite funny, and it gives you a good understanding how the objects in C++ are then implemented under the hood in C and in the machine code. Now, the other reason why using printf might be advantageous over using stdout is that it allows you more flexibility when formatting the text that you want to output. So in stdout is in a way simple because you can concatenate a lot of left shift operators with different types, and you have the right conversions implemented. But if you would want, for example, to specify a numerical representation, then in std that becomes slightly more complicated. I'm actually not sure whether you have the full functionality of printf available on your stdout. Probably yes, but in the end in a very convoluted way. So to make an example, if we have a variable int test is gleich 1, 2, 3, and you want to print it in printf, you just write %d, small d. Actually, you can use quite a few. You can use %d, %u, %i. What are the differences? We'll take a look on later on. But let's stick with %d, and then you can provide as an argument your variable, and this will print it just as a base 10 representation. If you want a hexadecimal representation, then you would write a null %x. So just %x means small hexadecimal, so 0 to 9 and small a to small f, or you can use large X to use capital letters in your higher 6 numerals. But what you also can do very easily here is you can write, for example, null 8x. So this will tell it that the number must always be at least 8 characters long, and if it's not, then fill it up from the left side with zeros. You can easily switch when using std to hex, but I would not remember off the top of my head how to tell it how many numbers you actually want to be printed. I'm sure there is some additional modifier that you could specify or something, or configure it some other way, but the nice thing is that here it's really easy. So for example, if you know that you have something that has x 1 2 3 4 5 6 7 8, and then you have another variable test2, which you know that it's only a to a b c d, a to d, then you can write test1 test2 space suck, and you are happy. Alright, let's go like this. And in using the std out, I'm pretty sure you would need to write more code to get the same result. Yeah, so that much to this question. Good. Now, since this is a 3-hour long lecture and exercise, technically we are expected. So the official time goes from 15 till 17:30. But that kind of, if you break it down to 45-minute blocks, shows us that it's actually 15 minutes too long. And the idea is that we should have made a break after two academical hours, which I forgot, and I often forgot that. So we can end lectures when possible without it. So you can tell me whether you prefer a break or to finish 15 minutes earlier. For me, it doesn't really make a large difference. Also, since we are running out of time for the first lecture, I think what will definitely interest you as well is some of the administrative stuff about the lecture. So as you know, it's a Vorlesung und Übung, so it's a lecture with exercises. In the part one, most of the exercises will be provided as homework. So the lecture will mostly be used for lecturing, and you will have to upload your exercises to Moodle. We will not spend much time on presenting solutions, so since we rather want to spend the time on new things. But if you find some particular homework particularly challenging or interesting, you can of course let me know, and then we can take a look into the solutions for this particular homework, as well as to take a look on the reference solution maybe. With regard to the notes that you will be getting, so there will be homework, as already mentioned, during the length of the lecture, which ideally should be turned in like not the next lecture, but the over next lecture. So you get the homework, you should try to do it, and with the next lecture, if you didn't manage to do it, you have the opportunity to say, okay, I went this far, that doesn't work, can you give me some hints? So then we can talk about it. I can tell you what you should try or what the problem might be. Then you have another week, and then it's the official deadline when the homework should be turned in. Effectively, if you turn it in even later, that will not be weight negative in your scoring. Although there are, of course, limitations, like if someone says that, oh, this was a particularly interesting homework, can we take a look on it, maybe make a reference solution during the lecture, then of course you cannot longer turn in the homework after the solution has been presented. So the only guarantee is the solution will not be presented within the first two lectures, but after, so this is the time you should be done with it. If not, it's on your own risk. If we go through the solution, then you are too late. So don't try to I'll do it later. If you can do it, do it. If you fail on doing it, you can try as long as you need to make it. And if you are lucky and there was no reference solution yet, then it will be accepted just fine. At the end of the lecture, there will be a final project, which you will need to implement. It will be rather large from the scope. So some of the homeworks will be really simple, some other will be less simple. The final project will be a bit bigger. And the idea is that the homeworks and the final project weigh the same. So if the total, so every homework in Moodle I think is valued, like you can give 1 to 100 points. So the amount of how many homeworks you get will of course depend on how far we progress with the material during the lecture. And the final project, while on the Moodle it's only also 1 to 100 points, will be multiplied by the amount of homework that was scheduled. So like half is the homeworks and half is the final project from the total amount of points that you will get for your final score. Another thing to be said about the final project and the homeworks is that they will always contain so-called optional parts. So you need to make the homework, the mandatory part of the homework, to get the 100%. But then there are the optional parts, which will give you bonus points. So if you would have a longer homework, which even may contain like a couple points, if you don't make like all of the mandatory points, but in turn make some of the additional points, you can then still get like the additional points and get the full 100 points for your homework. Also, normally the points are not just applicable for the current homework, but if you like make the first homework really good and get 100 points for the homework, plus you have 50 bonus points or 10 bonus points from the additional parts, then if you make the next homework just 90 points, then in the total evaluation, the points that you overachieved in the earlier homework will be used to fill up the missing points in the later homeworks that you might not have fully achieved. So the idea here is that to get a passing grade, you need to have at least 50% of the total non-bonus points, so the basic points 0 to 100. And to get a very good grade, it is necessary to have like 100 points on everything. So there are two things that conclude from it. First is, if you just want to pass and want to invest the least time you can, just to the final project, get 100 points and you are lucky, but that's a huge risk. If you don't get 100 points on your final project, then you will not pass. So it's really highly recommended to do all the homework. The more points you have, the better. And the second thing you learn from it, it's not that hard to get 100 points on everything, because with most of the homeworks, including the final project, you will get additional bonus points. So even if you completely fail to do 1 or 2 of the homeworks, you can still get a very good grade if you did the additional optional assignments during the other homeworks or in the final project. So I think what I want to say is just try to do as much as you can. Yeah. And don't be too worried if you would run at some point into something that you cannot do. Also, you can ask me at any time for advice. So you can contact me by email if you are trying to do something in your homework and it's crashing and you do not know why. You can write me, then we can take a look over Zoom, either at the end of the lecture or even at an extra date, depending on how many people request that. That will also be an option, and like asking for help is not anything that will be weighed negatively. So if you need help, just ask. That's basically the rule. Yes, so usually during the part 2, which is in the next semester, it is a bit more interactive, so you get also to do things during the lecture itself. I don't think we will have time in part 1 for things like this, but just so you know it, in case you want to take part 2 in the next semester, for doing things during the lecture, you would aggregate bonus points and just bonus points. So if you say, oh, I want to try, let me try, and then you screw it up completely, then it's as bad as if you just not do anything. So it's not really negative. You can only win bonus points, you cannot lose anything. And also there are no negative points for asking stupid questions, or as the saying goes, there are no stupid questions, just stupid answers. Yes, that much to this. Yes, to the final project, one more thing that should be mentioned. It will be scheduled like about a month before the lecture ends, and once it is scheduled, they will no longer be any homework scheduled anymore for the last 3 or so lectures. And ideally you should turn the final project in at the latest 1 week after the end of the semester. If you need longer time, let's say it like this. If it's more than 2 weeks after the end of the semester, the administrative personnel will ask me where are the grades So if it's just one or two of you and I have a good excuse from you why I'm letting you turn it in later, it will be fine. And the time you need to make it will not have an effect on the grade, just an effect on whether you get a grade or not at all. Or a bad grade. So I said if you turn in homework, which is enough for a okay grade, but don't do the final project, then well, it's up to you. You will not get a good grade, but you will still, if you have enough points, get at least a passing grade. Yeah. Any questions on this subject? Well, it depends on how far we progress. In general, we will really learn how C and C++ work from the low level until we really can write object-oriented programs in C++ using all the useful functions. So, as a simple outline, I have some internal note that I can paste into the chat. Where did I put that? Nope. Moodle is down today. It doesn't work. It's broken. It's something with the database. I can upload it as just remind me the next time. Then. Okay. So, but now for you. Let's see if this is complete. This is complete-ish. Modern C++ version, multi-threading APC. Well, I will paste you a list, but it really contains also stuff that will be in part 2. So this is more or less the whole plan. And you also see that on the beginning it's much more structured, and the further we go, the less structured it becomes. But we will definitely get to classes, exceptions, and do some of the STL containers and C exceptions. Modern C++ features, multi-threading, that is probably things that will be during part 2. Sockets, definitely. Databases, if we take them, then as well. In fact, in the last lectures, we never took a look into this because it's kind of less useful. The main focus of part 2 will actually be all the Qt stuff. So basically, which will allow you to create a nice UI. So like the not longer so low-level things about C and C++. But I will copy it into the Moodle once it's up and running again. Okay, what else? Yeah, I tend to talk very fast, so if you want me to slow down, you have to remind me of doing so, maybe even multiple times per lecture. I will upload the lecture to YouTube and put the link on Moodle for all the lectures that we will have. What else? Yeah, I guess that's that. And since we didn't have a break, we can finish the today lecture in 6 minutes from now, so it would be good if you would have a few more questions to fill up the time. If not, then yeah, then not. Then we also can finish a bit early the first time. I'm sure I will be overtime a few times in future, so we can start with some from a minus score in my overtiming. Yeah. Also, if you notice me going overtime, also just remind me. Then we will finish wherever we are. Yeah. Okay. So if there are, yes. There is one in the chat. Oh yes. Well, the first exercise will be due once I schedule it. I haven't gave you any homework yet, so I cannot tell you when it will be due. But I expect that we will be advanced enough after the first lecture that next week I will schedule you a homework, so it will be due 2 weeks from then, so it probably will be due 3 weeks from now. Okay, that's also not another good thing. When I'm talking and watching the Visual Studio and so on, I'm not watching the chat. So if if you have a question, just ask it, like with voice in person, because that I will notice because I'm hearing you all the time. Or if you see someone else ask the question in the chat and you see me not seeing it, then just like Thomas just did, tell me that there is a question in the chat waiting to be answered. So that would be helpful. Okay. Anything else? Mm-hmm. Yes. So here it's still open. You have the main CRT startup and then the invoke main call. Okay. Yes. Well, first of all, including headers is a computational intensive operation. So the more stuff you put in your headers, the longer your source files will take to compile. Now you actually offered here a special case. Let's put everything into a header and have one source file. You could do that and it would be in a way acceptable with regard to compile performance, but it would be quite complicated with regard to your code structuring because, well, there are two things. First of all, you don't want your files in general to be like hundreds of thousands of code lines and contain every conceivable functionality of every aspect of your program, because it will be just highly intransparent for the programmer, for you, for other people that might need to maintain the code later on. So ideally, you would want to break up functional aspects of your program into different individual source and header pairs. You might even want to have like maybe one header file and a couple source files, which each of them implements a certain subset of the functionality. It is just, in my experience, more easy to work with files which are not infinitely long, and where the file name also indicates to you what the file is actually doing. With just C, this is of course highly flexible. With C++, there is another consideration, namely that you want to have your object, your class definitions somewhere. And the recommendation here, for example, is that you have your class definitions always in your header files, and then to a header file, and then basically that the header file has the same name as your class, maybe minus some prefix. And then you have a source file for your class where you just implement all the actual functions for your class. So this already in a way gives you a how to say it, an intuitive guideline wherever to introduce a new source and header file pair whenever you start a new object, a new class. You would probably want to add some additional headers for configuration. So if you have some global preprocessor definitions which you want to use in many places, then this is something you would want to put into an extra header. What else? The other scenario where it is helpful to have multiple headers is if you in fact would have how to say it, as I said at the very beginning, in C everything that you use needs to already have been defined. So if you have a class which you define, and then you have another class which are using the first class, then this is fine. But if you would have like two classes, and these two classes which will be referring each other, so you have a, let's say, a class called parent and a class called child, and like your parent class of course has many children, but the children also have like a reference on the parent class and can do something with the parent class. You could effectively not write this in one header file, because then you have first your parent, then you have your child. The child knows the parent, but then the parent cannot know the child because the parent is already defined. So you have like a catch-22 scenario. What was there first, the hen or the chicken or the egg? If you split it into headers, the headers will contain only definitions but no functional code. So you can have your both headers, and then you can include both of the headers inside your child and inside your parent source files. And this way, the child will know its own functions and all the parent functions, and the parent will do the same. And then the functions within the child's source files can refer to the parent's functions and vice versa. In principle, you could put the definitions in your header file, then put the bodies of the functions below the definitions also in the header file, and end up with one huge header that contains everything. But that's like a thing you can do, like you can write a whole program in one line, but it's something you shouldn't do because it just severely compromises the readability of the source code and the project for people that later have to work with it, and also for yourself. So this is a real problem if you write a program with 10,000 lines of code 10 years ago. Unless you are have a really good memory after 10 years, unless you were like working on it all the 10 years in between, you will be really happy that you have written it in a easy to read way, because then you will kind of remember what you did. You will not really remember how it worked after a few years of not using it. So do yourself a favor and try to write code which is in a way self-documenting with comments, which is nicely readable. Yeah. It's not just for the behalf of other people that might need to work with your code, it's also on your own behalf. Okay, anything else? What do you mean? Visual Studio comes with a compiler. You asking questions? I have no idea. I'm old school. I write all my own code. I don't even want it to complete the quotation marks when I write a string for me. Um, I don't know. Check it. Try it out. Maybe there is. But that kind of would defeat the purpose of learning a programming language, right? Uh, you want to write the code during the lecture and not let an AI write the code for you, especially if you are learning it. Because, I mean, if you are prolific in a language, you know what you are doing, then sure, you can use some AI generated code, check it, and be reasonably confident that it will do what you want. But if you are learning a language and don't really know what it's doing, it will compile it will write some code for you, and you think, okay, it probably is right, so let's keep it, and then the code will do something completely wrong. So this AI assisted code generation is quite dangerous in my opinion. This is something you can do as an expert if you are writing something very quick and dirty, not for deployment. But I would not want to deploy something to the consumer or to your colleagues in the lab that may misbehave in an arbitrarily bad way. What you have in Visual Studio is IntelliSense, but this is a very basic feature. So if you start writing something, it will suggest you, for example, if you start with the global namespace, it will suggest you every, okay, I cannot scroll through it. It will suggest you every function or, well, variable or anything defined in a global namespace. If we later have C++ and to write the name of a function, like as I don't know, my object, and then dot or arrow operator, it will list you what members this object has. So there is some automation that helps you writing a code quickly, but not at the level of AI. If there is a plugin, I mean, as said, it's highly extensible. There might be a plugin for Visual Studio that adds Copilot, as Google, or nowadays Ask Bing. uh, if you already managed to get into the internal Bing trial, then you will see whether there is or not. But I would discourage the use of this Copilot feature when learning a language, definitely. Okay, Thomas, I think you also had a question. Mm-hmm. Yes. Mm-hmm. Mm-hmm. Yes. Mm-hmm. Well, first of all, I would not edit any of those programs. I would create a new project, but it can be as simple as you just copy all the source and header files into the new project, include them into the project, um, and write a new main function, comment out the old two main functions, and that's it. I just need a new main function that does the functionality of both. But of course, it will highly depend on the complexity. So the way you describe it, it sounds like you will have one header, one uh, source file, and that's it. But if you have more complex application, you have like 20 source files and half a dozen of header files, and in both of your projects, then it would be more advisable to try to move all the program logic aside of the user interface or aside of the main function to a library. So, I mean, in the simplest way, you could just go to Visual Studio. Let's stop this here. Right click here. So you would take both of your projects, put them into one solution so that you have your my test app 1 and then you have your my test app 2, and then you add your third, which will be your project. And for the two first ones, you go on properties, you go on configuration type, and then you just select DLL or static library. And then you need to comment out, of course, your main function in the two projects, and then you will need in your third project, which will still be an exe, to include some of the headers from your other two projects, and then include the lib files which you will be generating, and then this is the most elegant, most clean way to combine two old applications into one. Although here this also in a way let's say in a way expects that the applications did not really had much of a user interface to begin with, where they were more like in your example, just some console application that takes a few arguments and that's it. If you would have more advanced UIs in both cases, then probably what you would need to do is to take each of the applications on their own, separate the applications into a library and a UI. So an engine library, let's call it, and the UI. And then once you did this for both the applications, just take the both engine parts and integrate it into a third application, a new one, which would then provide a new interface that will do both of the things. This is not like this in C. What you can of course always do is you can write an application which will start the two other processes and pass the right arguments. But then you will have in total 3 processes running, which is not on Windows really good. So on Windows you have quite a overhead when creating processes. On Linux it's not so bad. So on Linux it is quite common that you just create a gazillion of child processes doing stupid things like sending a ping or listing your applications. So like running application in the system or whatever. On Windows you would really try to use the API and not invoke utility applications whenever you can use an API for doing it. But as said, turning an exe into a lib is reasonably easy. You just need to comment out the main function basically. Okay, any more questions? No more questions? Okay, then I guess it's time to end anyways. So we will see each other next week. I think next week is not a holiday. Let's check this quickly. Nope, next week is a normal week, so let's see each other next week, and maybe already have a nice weekend if you don't have anything on Friday. Bye bye.